Hi everybody, this is Arif. Today we will solve integrals, and we actually use integrals to calculate the areas of different shapes. We will start with something easy, and we will actually discuss two different methods. Okay, it's going to be quite exciting. So we will first start with a circle. Okay, it's easy. It's an easy one. I hope you all know what a circle is, right? Okay, so let's suppose this is my circle, given as x squared plus y squared is equal to r squared. So I want to find the area enclosed by this circular curve. Okay, so the first method, we use a strip, right? This differential element, which has a thickness dx, and the height is simply y of x, right? Okay, due to the symmetry, I have four pieces here, right? And each piece has an equal size. So the area is simply equal to 4 times y of x dx. So x changes from 0 to r, right? So this integral is nothing but the area in the first quadrant. Multiply by 4 gives me the total area. This is good. So what is y of x? 4 times from 0 to r. So y of x is nothing but square root of r squared minus x squared dx. Okay? So I take the positive root because y is positive in the first quadrant. This is good. Now we can use trigonometric substitutions. So it's easy. So when we say x is equal to r, say sine theta, dx will be equal to r cosine theta d theta. Okay. If I make this substitution here, this gives me 4 times. Look at the limits. So when x is equal to 0, theta is equal to 0. When x is equal to r, theta is equal to pi over 2. Good. So here, over here, I'll have square root of r squared minus r squared sine squared theta, and dx is equal to r cosine theta. So this is r cosine theta d theta. Very good. So then a is simply equal to, so I can take one r out. There's another one here. So this gives me 4 times r squared. Integral from 0 to pi over 2. Okay. Inside the square root, I have 1 minus sine squared. But 1 minus sine squared is cosine squared. Okay. Then I'll have the absolute value of cosine theta. However, in this domain, right, cosine is positive. So I can simply disregard this absolute value sign, and I have one more cosine here. So cosine squared d theta. Okay, so now I can multiply by 2 and divide by 2. Okay, this gives me 2r squared here. Okay, and 2 cosine squared theta is equal to, as you may all remember, cosine 2 theta plus 1 d theta. Okay, so the integral of this gives me a function like sine 2 theta, right? Sine 2 theta. If I look at these limits, okay, sine pi is equal to 0, sine 0 is equal to 0. So the first integral actually gives me 0. The second one is just 1. So this is just d theta. So this is nothing but pi over 2. So the result is pi r squared, as we all know. This is great. So I'll show you the second method, and it's going to be a lot easier than this. So the second method to find the area of this circle. Okay, for any curve, so you may have a curve like that. Okay, may define. So this is our origin. Let's say you may define a polar coordinate r. This is like the the magnitude of the, say, position vector. So if I make an angular displacement, but a differential one, so let's call it d theta, I actually create some sort of a right triangle here. So the differential area here just becomes 1/2 r d theta, because this length here is r d theta, right? So the differential area is nothing but 1/2 r squared d theta. So if I know how r changes with theta, okay, if I know how r changes with theta, the area is simply equal to 1/2 r squared d theta. So the limits may be from theta 1 to theta 2. Okay? Okay, so we will apply this here. Okay? So if I take an r, and this is theta. Okay? First of all, I need to be able to write this r in terms of theta for this circle. Okay, let's do that. So from this geometry, what we can say is this point has x and y coordinates. Using the trigonometric functions, r is equal to cosine theta and y is equal to r sine theta. So when I apply this here, what do I have is r squared cosine squared theta plus r squared sine squared theta is equal to r squared. So cosine squared plus sine squared is equal to 1. So this gives me r is equal to r. So it's constant, right? So what does this tell me? It tells me that whatever my theta is, the r, the distance from the center of the circle is a constant, right? Okay, so let's find the area. So it was 1/2 r squared d theta. But this time, this is 1/2. R is a constant, we can simply take it out, r squared. So how does theta change here from 0 to 2 pi? So you can simply multiply by 2 pi, this gives you pi r squared, as before. Okay, so as you see, this method turned out to be something much easier to apply. Now is the time to find the area of an ellipse. Are you all ready? Okay, this is good. So we will use the first method we use to calculate the area of a circle. Okay, so I picked a differential element here with some thickness dx and height y, and this is my ellipse equation. So I assume that a is larger than b here. In other words, the major axis is on the x-axis here. Okay, so using this equation, I can write that y is equal to b times square root of 1 minus x squared over a squared, right? So I assume y is positive in the first quadrant. So I'm just looking at the first quadrant here. So in the end, the area will turn out to be 4 times y dx, right? X will change from 0 to a. So this is what I want to calculate. So the area would be equal to 4 times. So y is this, b is out, it's a constant, integral from 0 to a, square root of 1 minus x over a square dx. Okay, good. So here at this point I can make a substitution, x over a is equal to sine theta, like a trigonometric substitution. So dx will be equal to a times cosine theta d theta. Okay, so the area would be equal to 4 times b, the integral. So when x is equal to 0, theta is equal to 0. When x is equal to a, theta is equal to pi over 2. This is how we determine the limits of this integral. Okay, and then square root of 1 minus sine squared theta, which is cosine theta, absolute value cosine theta, but it is positive in this domain, so you can simply take it out as cosine theta. So I have a cosine theta d theta for dx. So this is a, this is cosine squared theta d theta. Okay, very good. So I can simply take this a out, right? and I can multiply by 2, divide by 2. So this gives me 2 here, factor of 2 here, and then the integral from 0 to pi over 2. Okay, so this is nothing but, so a is equal to 2ba times 2 cosine square theta. As usual, we have cosine 2 theta plus 1, or not over 2. So cosine 2 theta plus 1, because we already have 2 here, d theta integral from 0 to pi over 2. Okay? As we discussed before, the first term, the integral of cosine 2 theta, is going to be 0 in these limits. So I just have d theta here. So this integral is nothing but pi over 2. Okay, so the area of an ellipse is pi times AB, as you may know. Okay, I'll clean the board and I'll show you how the second method works. Now we are ready to apply the second method to find the area of an ellipse, okay? So in other words, we'll be using polar coordinates, r and theta. So as usual, r and theta are related to x and y coordinates, of course. So using the definitions of sine and cosine functions, we can write x as r cosine theta and y is equal to r sine theta. Okay? So using the ellipse equation, you can simply write this as r squared cosine square theta over a squared plus r squared sine square theta over b squared is equal to 1. So at this point, I'll multiply everything with a square and b square. So this gives me b square here. And this gives me a square here. And on the right hand side, I have a square, b square. This is good. So the next step is, you can put r square out. So you'll have b square cosine square theta. Just remember that a is larger than b, right? So in this a square, I'll just separate a b square term, just to match this one here. So I'll have b square sine square theta plus what is left is a square, right, minus b square sine square theta, okay, is equal to a square b square. This is good. But what is this? B square cosine square plus b square sine square. It's just b square, right? Because sine square plus cosine square is 1. So this is just b square. There is an r square here. Okay, at this point, I'll divide everything with b square. So this just gives me 1. This is nothing but a square over b square. So this is a minus 1, and this is just a square. See, we are simplifying the expression a little bit, right? So at this point, I'll define a new parameter. So a square over b square minus 1, I just call it c square. And I already know that it's positive, right? It's not imaginary, it's positive, because a is larger than b. Okay? This is how I oriented my ellipse. So this is just c square. Okay. I do not like to see the powers of trigonometric functions, right? Is there an easy way to turn this into a function of theta? Yes. Yes. So 2 over 2, right? So what is 2 sine square theta? As you may remember, cosine 2 theta is equal to 1 minus 2 sine square theta, right? So using this double angle identity, you can write 2 sine square theta as 1 minus cosine 2 theta, or 1 minus cosine 2 theta. Yeah. So this is nothing but c square times 1 minus cosine 2 theta. Okay. So now I can multiply everything with 2 maybe, to make things easy. So this becomes 2. This becomes 2a square, right? Now we are ready to write down what r square is in terms of theta, right? So r squared is nothing but 2a squared over 2 plus c squared. Then I have minus c squared cosine 2 theta. Okay? And this is my r squared. Okay? So as you may remember, I need to integrate it over theta. And there was another factor of 1/2 in front. So this is what we will try to calculate now, d theta integral. Okay, I'll clean the board a little bit and then we will move on from here. So in the last board, we ended up with this integral. So I put the limits from 0 to pi over 2. So I'm calculating the area in the first quadrant. I multiply with 4 to find the total area. So I have 4 pieces here, right? So this is the integral I want to calculate. So before we move on any further, I'll make the substitution. So I want to get rid of this 2 theta here. So I'll just make it simpler. So this is just alpha now, right? So d alpha will be equal to 2 d theta. So this becomes 2. Instead of d theta, I'll have d alpha here. So the limits also change. So this is 0. This will be pi, right? So the new limits here. Okay. So as you may remember, it is tricky to find to evaluate these type of integrals, right? Whenever we have cosine or sine functions in the denominator, it's a little bit tricky, right? I'll put a link here. You can go ahead and check how we managed to evaluate these integrals. So we used tangent half angle substitution. So what was that? So you would define a new parameter here as t is equal to tangent alpha over 2. So if you define it this way, dt becomes 2, or d alpha becomes 2 dt over 1 plus t squared, and the cosine alpha is equal to 1 minus t squared over 1 plus t squared. So we'll make these substitutions here. Since we do not have any sine alpha, I didn't write the sine alpha term here. But please go ahead and check the video where we discuss this substitution in detail. Okay? This is really helpful. So the area integral becomes 2 times a squared. Put a squared out. Integral. So d alpha is 2 dt over 1 plus t squared. Okay? This multiply with, I have 2 plus c squared here, minus c squared. What is cosine alpha? 1 minus t squared over 1 plus t squared. Close. And then this is what I want to calculate. Okay, so when I multiply everything with 1 plus t squared here, I have this term. Then I have minus that. Okay. A nice simplification. So this becomes 4 here for a square. So let's collect all the t squared terms here. Okay. So t squared, let's write it down here, 4a squared integral dt over, let's look at the constant terms first. So 2 plus c squared, this is a constant from here. The other constant here is minus c squared, right? Minus c squared. This is good. Plus, let's look at the t squared terms. I have 2 plus c squared here. And the t squared term here is plus c squared. Okay? Very good. So what is this? So c squared minus c squared is equal to 0. So this is just 2. So I have 2 here. So what is c squared plus c squared? 2c squared. So this is also 2 here. So I can put a factor of 2 out. So this becomes 1 plus c squared, right? But what is 1 plus c squared? It's just a squared over b squared, right? So this is nothing but a squared over b squared. Okay? So you can put 2 out, 2 parentheses. In other words, you simply divide this by 2. Okay, so now we have quite a nice expression here, right? So, okay. So in this case, what are the limits? Okay, t. So when alpha is equal to 0, okay, t is equal to 0. So this is the lower limit. What is the upper limit? When alpha is equal to pi, tangent pi over 2 is simply infinity. Okay, very good. So at this point, we can make a u substitution, as you may agree. So you will say a over b t. So u is equal to a over b times t. So what is du? A over b dt. Okay, very good. So instead of dt, I can write b over a, right, du. So when t is equal to 0, u is 0. When t goes to infinity, u is infinity. So the limits don't change, right? And here, this becomes just u squared. Okay? So I can take b over a out. So this gives me 1b here, and I can divide by a. Okay? So what is this integral? This is nothing but arc tangent u, right? So this is arc tangent u. The limits are from 0 to infinity. So these are the limits, right? Okay. So what is the upper limit here? Arc tangent infinity. Pi over 2, right? So this term here is pi over 2 minus arc tangent 0 is simply 0. So pi over 2 minus 0 is pi over 2. Pi over 2 times 2ab is equal to pi times ab. And this is the result. It's the answer. Okay? So as you see, in this case, using the polar coordinates was a little bit trickier, a little bit harder. I hope you enjoyed the video. We will solve more problems in the future. See you later, guys. Bye.